conduction band is called energy gap. That's what I have.
Okay. So apart from answer as energy gap, any different answer at all?
Sir,
Mm-hmm.
I think it's the electron hole pair.
Okay. Can you justify that, I beg?
Because the question is asking when an electron jump from, it has been able to jump. The question is not asking of the how it jumped. It has been able to jump. It has moved to a different band. That is the conduction band. And he said, what does it leave behind? What does it leave behind? Like that, when the electron leaves its position, it has left its position. So there will be a space, like you are sitting in a classroom and you left that position to sit at a different place. You have left that place to become vacant for another person to come and occupy. So that is what happened.
Okay. So apart from answer as energy gap and electron hole pair, any different answer at all?
Please, when I choose hole because I saw that when an electron gains enough energy and then it jumps from that place, it leaves a hole there.
Okay.
It leaves a hole at the at where it has jumped from.
Okay.
That is why
That's
I
fine.
choose hole.
I think this question is very confusing because of what it asked. Because it asked, what is this gap called? It leaves a gap. And it's very confusing. The actual answer is CO, as Madam Felicia said. CO because any electron transits, it doesn't leave a gap at all. A gap is it's a space like a band. And electron movement cannot leave that kind of a gap. Is that okay? But when it leaves a hole behind it. Is that okay? You can try to choose electron hole pair, but that one deals with ionization. We are talking about a lot of these elements or atoms. And it will be very confusing to choose electron hole pair because it's correct in a way, but it's not correct. It's not correct because we are not talking about the movement of electron and it occupying another hole on its own. Is that okay? And that one we can, of course, talk about electron hole pair. But since the question didn't state that, we have to go on to hole because anytime an electron moves, the only thing that it leaves the valence shell is a hole. Is that okay? So not a gap, like energy gap. Sir Michael, are we on board?
Yes, sir. I understood, sir.
Mm-hmm. So please, can someone help me? Number 2.
Okay.
Okay,
You said
go for number 2.
You asked me to answer it.
Okay.
Okay.
Sir,
So can you?
so elements with 1, 2, or 3 valence electrons usually make excellent conductors. Why? Because we just learned that when the atomic number increases, it also leads to an increase in neutron number, which affects the ability of the electrons to easily leave the valence shell. So when the valence shell has got 1, 2, at most 3, the attractive force from the electron from the nucleus is not that strong. Please get a feedback. It's not that strong. So because it's not that strong, the electrons can easily move from the valence band and easily move to the conducting band for conduction to take place. I think they are conductors.
Okay. So any different answer, Sergio? Thank you very much. Any different answer apart from Sergio's own? Does it mean everyone is going in for D, conductors?
Yes, please.
Okay.
We are
Yes,
going for
I
conductors.
Mm-hmm.
And per my this thing, per my should I say,
Explanation.
per my understanding or explanation, I know that when there's a list number of electrons, let's say starting from 1, 2, 3, on the valence electron or on the valence shell or the outermost shell, that that particular atom is likely to what? To lose electrons. And as it loses, either it loses the 1, 2, 3, automatically it becomes what do you call a metal in most cases. And metals are conductors. So I will pick conductor.
Okay, that's perfect. So the answer for this particular one is conductors. Is that okay? Now let's go on to the number 3. Can someone help me with this? Say, Mark, have you answered the question?
No, sir. Okay.
Okay, sir, let me help out with. I'll answer the question. So the question is, it is asking you what is the primary reason for electrical conductivity of a metal. So the answer. All I've said, the answer is
Yeah,
0.
we are listening to this.
The answer is 0, sir.
The answer is where?
The answer is C. Let me
See,
see.
okay.
So the answer is 0. 0 to me. But I see the answer to be 0. So.
I don't see 0 here. The question 3 reads, what is the primary reason?
So he was selling, so he's confused with his selling and then the answer.
Hey,
Okay, so Sir Rabbi,
so the answer is please let me finish. What's the primary reason for the electrical conductivity of a metal? So I believe they lack free electrons in the conduction band. That's how I see it. Sir.
Okay. Thank you,
okay.
Sir Francis. Sir Mark, can you come in? Sorry about that.
Yeah, I also think that what is the primary reason for the electrical conductivity of metals? I'll go in for B. The overlap of the valence and conduction bands. Now, if the valence and the conduction bands are overlapped, then the valence electrons are free to move at any time from the valence band to the conduction band, and that causes the electrical flow of conductors. So I'll go in for B.
Okay, so any different answer apart from Mark's own? So we want the primary reason why, of course, conductivity happens in a material like a metal. Is that okay? And
okay, sir.
Yes.
Yes. I also go for B, which is overlap of valence and conduction band. In general, the three types of material we talk about over here is very clear that naturally they may have an empty conduction band naturally. So in the case of the overlap of the valence and the conduction band, less energy is required to move from the valence band to the conduction band. So that is why, yes. So for that reason, we can say primarily electrical conductivity may depend solely on the gap due to the minimum energy required to cause that electron to jump from the valence band to the conduction band. Thank you.
Okay, thank you very much. Any different answer apart from answer? Okay. So now let's move on to the next question. Thank you very much. Number 4. I want a different person to help me answer this. Ibrahim, have you answered any questions so far?
Yes, please.
Okay. Benedicta, Madam Benedicta, can you come and answer this one for me?
What happens?
Oh, she's not online. Sir Desmond, can you help me answer this? Hello, the Sir Desmond. Eric Asamoah. Is it Asama? Asuma, sorry. Sir Eric.
Yes, please.
Can you help me answer this?
Question 4.
Yes, question 4.
Okay, so what happens in a semiconductor when energy is supplied through heat and or light? I think
Is it my network? I'm not hearing anything.
hello.
Yes.
Yeah,
I
we
said
can hear you, but we cannot hear him.
Okay. Sir Eric, your line keeps on breaking. We can't hear you from this end.
I said the electrons move from
Eric,
valence band.
it seems your network is breaking.
Electron moves from where?
I think he's picking B. Electron move from the valence band to the conduction band.
Okay. To the conduction band. So apart from Eric's answer, any different answer, I beg? Okay. So this is correct. And I told you that for a semiconductor, it actually plays or stand between a conductor and an insulator. Is that okay? Depending on what is going on with it. So if, of course, we apply some energy to it in the form of, say, heat or light or anything, any EM field, it will actually get the chance to eject some of these electrons at the valence band to the conduction band. Is that okay? And that will let it even be more of, say, like a conductor. But it will not reach a conductivity range, but at least it will be like a conductor. Is that okay? If energy is applied to it. Now let's look at the number 3. Sir Clement, can you come on board? Not online. Okay.
Okay, Rabbi, are we looking at number 5 or number 3?
Number 5. We are done with number 3. So, John, Sir John. Yes, Sir George.
Okay, sir.
Hold on. Clement is online. Let him answer it for me, I beg. Sir George. So hold on for a
All
bit,
right.
I beg.
Hello. Yes.
Yes, please.
Number 5. In a semiconductor, what is created when an electron from the valencing band moves to the conduction band?
What to be the answer for this, I beg?
I think it will be an ion.
Okay. So no, we are talking about when electron actually moves from a valence, is that okay? And goes to the, what does it leave behind? Here, you can justify ionization state, is that okay? But here we are dealing with conduction and valence band and the Fermi energy level and even the energy gap, is that okay? So when, say, at a place, then you move, what do you leave behind?
A hole.
Very good. It's a hole that you leave behind. Is that okay? So when you're talking about semiconductor, ionization cannot actually play a role here. Is that okay? Someone can actually justify it to do. Now let's answer the last one so that we can move on. Sir George, maybe you can help me answer this.
Sir, please, the difference between the first one, that I think the first or second, that we said it is the electron pair, and this one, there's a slight difference between the questions, or they're actually the same and the answers are the same. Because that is why that one, I was doing a little bit of reading, and I found that one is rather supposed to be the electron hole pair, but If they are the same question, fine. But I think that there's a slight difference between the question.
So what we have here is almost the same, but I think it's just a small twist. Is that okay? So we are just talking about still the movement of an electron from a valence to a conduction band and what is leaving behind. Is that okay? The first one, the small changes was about the gap, which was just to confuse you. But this time around, we are just talking. It just went straight to the point. Is that okay? But at the end, we are talking about when it leaves, what happens, and what does it leave behind. Is that okay? And of course, it's a whole that it leaves behind. So let's go to the last one. Sir George, please, are you okay?
So,
Mm-hmm.
okay, I'm okay. What is the
so let's
energy
look at
gap?
the last one. What is the energy gap between the valence band and the conduction band in an insulator? Is it going to be narrow? Is it going to be wide? Is it going to be zero? Is it going to be moderate? Yes, Sir Eric. Sir Eric Ofusu.
I think it's going to be wide.
It's going to be wide. Is that okay? For an insulator, it's going to be very, very wide. Of course, for a conductor, we expect it to be what? Overlap. And for a semiconductor, we expect it to be relatively very small. Is that okay? Or narrow? Now, if we are all okay up to this section, permit me to go on to the next one. Now, what we have here is still the explanation of what we've done. When you're talking about, say, particularly, say, insulators. And, I explained the fact that for a valence band in an insulator, the electrons there doesn't move at all. Is that okay? And because the neutrons is holding it very firmly down there, and it will let a very wide gap come in between the valence band and our conduction band that we have there. Is that okay? So at the end of the day, the valence band is very, 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 very big. Is that okay? The energy gap or the valence band or anyhow that we have to call it, or the energy gap or the band gap is very wide, and of the forbidden band is very wide. Is that okay? Because the electrons at the valence are not moving at all, and they are being firmly held by the nucleus, and even at ordinary temperature, is that okay? Like a room temperature, all the electrons are being fed by this valence band. It's not going anywhere still. Is that okay? And we don't have any electrons at the conduction band at all. This is three important properties that you have to know. The first one is the electrons are fully filled at the valence band. When we go and look at the conduction band, there is no electron at all. And when you look at the band that we have between the valence and the conduction, it is super, super wide. Is that okay? Now, let's look at something again, like the conduction band. The conduction band is not the same as how we saw the the insulators is. The conductors are very, very different. When you're talking about conductors, we are talking about the overlapping of it, which you know. Is that okay? We have the conduction band and the valence band are overlapping. See some electrons at the valence and some electrons at the conduction band. Is that okay? And of course, they can just be moving that in the world. Is that okay? And when you're talking about the conduction band, of course, one thing that we have to know is their resistivity is very low. And even when we increase temperature, it's still, of course, low. Is that okay? Which I think if there's a need, we will dive into it very much. This is just, and I just did this plenty right for your understanding when you are reading. Is that okay? So when you are reading, at least you understand what everything that I'm trying to put across. Now, when you're talking about semiconductor, that is the most important thing in here. The space between the conduction band and the valence band is relatively small, And as I said earlier, a semiconductor can actually behave like an insulator with some conditions. The same way the semiconductor can also behave as a conductor with some conditions. And if you remember, we solved one question where the question is saying that if we give it energy, what is happening to the electrons at the valence band. Is that okay? And it's very important. Then you have to know that this temperature is very dependent on this kind of a material. Is that okay? Please, are we following?
Yes, sir.
Very good. Now, let's look at low temperature. At a very low temperature, we expect that the electrons will complete at the band. Is that okay? And of course, the electrons there will not accelerate. Is that okay? It will just be staying at the valence band. It's a temperature like a room temperature, or let's say any form of a heat.
Hello, Bernard. Please mute your mic.
Or light. Is that okay? Any form of energy. This time around, the electrons that we have at the valence band tends to escape from there and goes to the conduction band. Is that okay? And that is what we are talking about here. Because at a condition, the semiconductor is behaving as an insulator. At the same different condition, the semiconductor too is behaving as a conductor. Is that okay? So you see, at room temperature now, the electrons that we have here, it will tend to escape after but it has gotten some energy. Is that okay? And now, when we tend to increase the temperature again, of course, the conductivity of the semiconductor will increase. And it will also increase with temperature because there's a movement of something going on there. Is that okay? But what even if the conductivity increases, the conductivity will never reach the conductivity of a pure conductor. Is that okay? The conductivity reaches to the extent that, yes, we have some electron movement that is going on in the material, but it will not be as a conductor. Is that okay? But at least we have it behave as a little conductor, maybe. Is that okay? So it's very important we know this. Is that okay? So it doesn't mean that if you have a semiconductor, you can actually tune its whole process to behave as a conductor. It cannot be like that. But at least as far as we have some electrons moving, it can be sub-categorized as a conductor one way or the other. Please, am I making sense a little? I'm confusing us.
Yes. You're making sense.
These materials, like the semiconductors, like the conductors, like the insulators, they all have a particular resistivity range. And of course, we expect that an insulator will have a very big resistivity, is that okay, as compared to, say, a semiconductor or, say, a conductor. Is that okay? Now, when you look at insulator is having a resistivity, we're talking about 10 raised to the power 5. We are talking about the conductivity, a conductor's resistivity, very, very low. Is that okay? Because there's no resistance going on. And that is at least as 10 raised to the power negative 3. And of course, the semiconductor is in between the two of them. That is 10 raised to the power negative 3 and 5. Is that okay? So it's very important we know this. And when you're talking about resistivity to the unit is ohms meter. Is that okay? It's not ohms. Ohms is resistance, resistivity is ohms meter. And I think there's even a relation that compares the resistance, resistivity, area, and length. Do we know that formula? Do we know a formula like that?
There is not resistivity is equal to lambda is equal to rho A over L. It's not that one, please.
Let's be very precise about the formula. There's a relation between resistance, resistivity, A, and L. Do you remember?
Yes.
Mm-hmm.
Yes, sir.
And I'm saying that
Yes, give me the formula, I beg.
it's not lambda equal rho A over L, or I'm wrong.
Lambda equals
Arrow A, capital R, capital A over L.
Over L. Can someone confirm this for me?
That's resistivity is equal to resistance times area over length.
Okay. Abel, can someone confirm this for me? Any different answer?
It's quite similar. I think it just made the R, what's the name, the lambda the subject, but it can otherwise be stated as R, which is the resistance, equals rho over A,
Okay.
where rho is the resistivity. So it's resistance equals resistivity times the length all over area, which is A.
Okay. So let's look at the most important thing. We are gradually entering into electronics. Now the semiconductor. We are putting aside the insulator, we are putting aside the conductor, and let's focus purely on what we call the semiconductor. And when you're talking about semiconductor, a very common material that comes into mind is like the silicon, like the germanium, like the gallium arsenide, and other things. Is that okay? And this one that we are talking about, of course, as I said earlier, has a property between of a conductor and what that of an insulator. Is that okay? And they are not good insulator, they are not good conductors. So they are semi-what conductors. And a pure core of these things can actually be seen as this. So I just checked online and I placed some pictures here so that you understand it. I have down here how the lattice crystal, and I'll talk about this today. And now let's look at something here. So if we have a pure semiconductor, it is there and nothing is actually influencing its ability to conduct or be an insulator. Is that okay? But interestingly, if we have a semiconductor, we have the ability to control its conductivity. Is that okay? And we can do that by adding something we call an impurity to it. Is that okay? And we will look at that one too. So if we add an impurity, of course, we can actually tune the way that this semiconductor will behave as a conductor. Is that okay? And it's a very nice phenomenon when we are talking about a semiconductor. If we do that, we call it doping. Is that okay? And this is just a process of just increasing the number of electrons or the number of holes. And when I say increasing the number of holes, I mean finding a way to remove some of the electrons in it and just leaving it as it is, so that at least as someone as where there will be electron hole pair. Is that okay? So as the electron occupies the hole, it leaves another hole behind, another electron to occupy that hole, it leaves another electron, and at the end it will let the electrons be moving in that particular material. That is one way. Another way too is to also increase the number of electrons. Is that okay? So if we have excess electrons, of course, we can also be termed as what? As doping. Is that okay? And this doping is not like taking a same ratio of the doped element and the doping element. Is that okay? It's just a taking of one order of the impurity to a millions of them. Is that okay? And here is about 10 millions or more of that particular semiconductor. So when you take a semiconductor like a silicon or a germanium, at its pure state, we call it an intrinsic semiconductor. Now we want to dope it. When we are doping it, it means we are increasing the number of what? Acceptors or donors. In other way, we are increasing the number of what? Electrons or holes. Exactly. So it's very important to know that. When we are doping, we are just talking about just adding one impurity to 10 millions of these atom of one. Now, I think I'm moving fast. Please, can you understand? Can I move on?
So you can move on.
Great. I think this area is familiar, so maybe there will be no problem at all. So historically, one of the most used at first semiconductors was the germanium. we're using germanium a lot, and as of now, it has been replaced with silicon, and because silicon has a very wide energy band gap, and as we have different materials of a semiconductor, they also have different properties of its own. And one particular property is their energy band gap. Is that okay? And the energy band gap of this particular material is very important, because if you take one that the energy band gap is relatively small, it means at a very small temperature, the material will behave differently as you want. Is that okay? But interestingly, silicon came to remove germanium one way or the other, because right now we are using it more because of one, its accessibility, and two, most importantly, because of what? The wide energy band gap that it has. So even if you increase the temperature, it will be very hard for it to transit easily to a conductor. Is that okay? And I explained the fact that if we have a semiconductor, and temperature is one important property that can let it be a conductor. Because when it gets temperature, it can actually move from the valence band to the conduction band. Is that okay? Now, if I have a silicon and I have a relatively wide energy band gap, even at high temperature, at least I can also still be using its application to say I want a different thing or something. Is that okay? So that actually brought the existence of silicon into its wide usage as compared to the germanium. Is that okay? There has been a lot of these semiconductors as we are growing, or the world is going on. We have some of them that we've combined different single elements together. And when you look at the examples that I have up here, you see there are two elements of a semiconductor that it has been fused together, like the gallium arsenide, like the indium phosphide, like the silicon carbide, like the silicon germanium. Is that okay? They are all one with the other, some difference in semiconductors. And most of the times we call them synthetic semiconductors because it's kind of created in the lab. Silicon we can mine for silicon. Is that okay? And extract its original core. But this time, after extracting, we combine some of them and we form different types of what? A semiconductor. Now we have, and when you combine the two of them, you call it a compound semiconductor. And it has a lot of applications, like the LED, like the lasers, like the photodiode. And now, everything that we are doing, LEDs are around. You go and buy a bulb for your room, LED is inside. Your phone, LED is inside. Your laptop, LED is inside. Everything, LED, exactly, because it's very cheap and it's very convenient. And it's through this that we have something like LED. It's through this that we have something like a laser. It's through this that we have something like a photodiode. Is that okay? So now let's look at the elemental semiconductors. When you're talking about elemental semiconductors, we are talking about semiconductor that is of only one element. Is that okay? We have the single ones and we have the compound semiconductors. That one we combine two semiconductors to form a compound semiconductor. And we have a ternary one. That one we combine more than two. Is that okay? It can be three different ones that we combined. And a very typical example of these semiconductors is the silicon, germanium, and SN is what? Which element is SN? Do we know?
Not two.
It's what?
Two.
Okay, that is them. Great. Compound semiconductors. So compound semiconductors, we are combining two of these elemental semiconductors. Is that okay? And most of the times, what is we take the one that is at group 3, combine with the one that is at group 5 to form these compound semiconductors. And of course, we can take that one of 2 and that of what? 4. Sorry, this is 6. Group 6 to form another compound semiconductor. Exactly. So this one and this one are interchangeable. A good that is the compound semiconductors is the one that I gave examples of earlier. Now, can actually talk about the mercury carbamide telluride. Their names is very, very confusing. So, anyways, I'm not sure there will be a question for us to give an example, but it's just for understanding. Is that okay? That we can combine three semiconductors, elemental semiconductors, to form another form of a semiconductor. And we can combine two of them to form another form of a semiconductor, or we can have only a single ones. Now, I told you that their energy band gap or the band gap energy is very important. Uh, and all the semiconductors has its own energy band gap. Is that okay? So when you look at silicon, you see it's different from that of germanium. And I told you silicon has a wider one as compared to germanium. Germanium is about 0.66. Silicon is almost like 2 times of that of the germanium. Tin is about 0.082. And everything that you do, you have to consider the energy band gap that will influence you on the application of these particular materials. Is that okay? Whether what you are doing, maybe it will you'll be able to control heat, so you need a smaller energy gamba. The ones that you are doing, heat is very easy to be on the board that you are building, and because of that, maybe it will influence the state of the material, like a silicon and germanium or the tin. So maybe you take for a bigger wide band gap so that it will not influence the material's property and other things. Is that okay? So it's very important.
Oh, no, sir, I can hear your voice.
Yes. Hello. Are you saying something? Please, can I go on? Or you are saying something?
So your voice was breaking. At times it will come, at times it will be faint, and it's difficult to hear.
Oh, sorry. Okay, so but you've heard all these ones, right?
Yes,
Yes,
sir.
sir.
This one.
Yes.
Okay. So maybe I will take my time so that when it breaks, at least we can still catch up. Now let's look at another important thing, still on the semiconductors. But this time around, let's look at the structures. A very typical example of a semiconductor that we've been mentioning is the silicon. And silicon has how many atoms? 14, right? And at the end of the day, we're expecting four valence what? Shell. Four valence electrons, sorry. And at the valence, let's look at something. At its pure state, these silicon bonds with other silicons for it to be very strong. And this kind of a bonding, we call it a covalent bond because the silicon has four around it. It will take another neighboring four and it will share the four of 8 valence electrons to it. And the neighboring ones to also share 4 valence electrons to it. So at the end of the day, they all have a very stable valence shell. And this is what we call the silicon crystal lattice. Is that okay? So in a pure material like an intrinsic semiconductor of, say, a silicon, this is how it behaves. Is that okay? They are bound together by a covalent bond, and they are very, very strong. Is that okay? When I say strong, I don't mean the strongness in the material's physical strongness. Is that okay? The strongness in terms of the covalent bonds. Is that okay? When we are talking about this, we see we don't have any free electrons that is actually moving in here. We can, although we can let some free electrons move here by applying heat or something, but ideally, you see this one, there's no free electrons. And for this type of a material, we can say it's a what? It's an insulator. Is that okay? And we can actually, again, decide on the conductivity by letting it be a donor or an acceptor, as we said earlier. We can entropy, which we will talk about it. Is that okay? End of the day, what we have to know is if we have a material like this we are talking about a very pure state of a silicon. Is that okay? And we can say it's an intrinsic crystal, and therefore there's no free electron that is actually moving. Now I wrote something here that if we do something like this, we can of course create a positive and a negative hole in it. Is that okay? And we can allow electrons to actually flow through this kind of a material. But at the end of the day, there's no way that we can let it reach a pure conductor. Is that okay? But we're still going to be in the range of a what? Of a semiconductor. But of course, we are increasing the conductivity one way or the other. Is that okay? And that is what we do by doing the doping, which I'll be looking at in the next, I think, 2 slides. But before we do that, we try this one too for me to know if you understand what is going on. Any questions so far before I go on?
Hello, sir.
So you would like if you can position
Please, I have a
yourself
question.
after the trials because your line keeps breaking from this and the slides keep going off.
Oh, sorry about that. Okay. Yeah, Sir George, I'll do that.
Sir,
Yes,
please,
Sir
would
George.
you explain a bit on intrinsic and extrinsic semiconductors?
Oh, okay. So
Yeah.
we are about to intrinsic. When we are talking about intrinsic, we are talking about the very pure state. And when I say the pure state, we've not doped it. Is that okay? They are all semiconductors, like a silicon that is in there, and they are bonded with a covalent bond. Is that okay? And I said earlier, it's going to be strong. And it's not the strongness as in the physical strongness. It's about the bond. Is that okay? And we say it's in its what intrinsic state or intrinsic crystal. We can say it's an intrinsic semiconductor. Is that okay? Immediately you introduce a different material like an impurity, either being an excess, creating an excess hole or creating an excess electron, that becomes an extrinsic semiconductor. Exactly, which we'll be looking at it in the subsequent slides.
Thank
Josh,
you,
are
sir.
you okay? Mm-hmm. So now let's just use 3 minutes to solve this one for me. Right now, please. Okay, please do that. Hello.
Hi.
Yes, sir.
Hi, yeah, we are here.
Hello, sir. Hello, sir.
So, Sir Francis, will you help me with the first one?
The first question is asking us the type of atomic bonding most commonly in semiconductors. So I believe it is covalent. D. I believe it's covalent bonding, sir.
Why do you use the word I believe?
Okay, I know. I
Okay, so that is going to be electrons.
I know it's covalent bond is
This is a state of what we know. This is not a believer thing, and like this is what it is. So, anyways, thank you, Sir Francis. So the second one is going to be what? Sir Ibrahim, will you help me with it? Okay. Sir Francis' hands is up. Fire minister. Yes, please go on.
The energy gap in a semiconductor does not change the temperature.
Come again.
Does not change the temperature.
Does not change your temperature. Okay. Ibrahim, thank you, Sir Francis. Hold on, let me ask if there's a different answer. Yes, Sir Mark.
Yes,
Uh-huh.
the energy gap in a semiconductor will definitely decrease with temperature.
Okay. So it will decrease with temperature rather. Is that okay,
Yes.
Sir Francis?
Sir Rabbi,
Yeah, Sir Mark.
I think there are two Sir Marks here because anytime I
Uh,
raise my hand and you call Sir Mark, one Sir Mark, my other Sir Mark will try to also
uh,
answer. So
so maybe I'll address you with your surname if you don't mind.
yes, I think that
Okay.
that will help.
Okay.
Thank you.
You're welcome, sir.
Sir,
Yes,
please
Sir
have
Joe.
a problem with this question.
Uh-huh.
Is it that
With
the energy gap decreases or the electrons are now excited that they now have enough energy to overcome the energy band?
this is a very interesting question
So
because at the
so
end of the day, yes, uh-huh.
so sir, please, what was his answer? I think I didn't get his answer. Well,
The answer is C.
C. Okay.
The gap actually
All
reduces
right.
with temperature. Is that okay? So anytime the we anytime a semiconductor gets a form of energy like heat, we expect the electrons at that particular valence band, of course, to be able to move at the conduction band. And as they move, it tends to reduce the band that is there. Is that okay? So at the end of the day, the energy band gap will reduce as with temperature. Is that okay? So it's very important.
Yeah, so it's
Can
not that they get in enough energy or they get excited.
so they get excited, tend to move, and at the end of the day, we reduce the band. Is that okay? So as
So
they
it
are
means that
moving,
two things happen.
yes,
So two things
it's
happen
starting from
as they are getting energy to move to the other energy level. The energy
yes,
band is also okay. Thank you.
yes. So, because at the end of the day, the energy level is going to be reduced. I told you that if you want to reach the energy level, is the highest energy level that electrons can reach when it has absolute zero. And this time around, it's not at absolute zero. It has a particular temperature, like a room temperature. That is not absolute zero. Is that okay? So, in that sense, the Fermi energy level is not going to be the same as it was. Is that okay? It's definitely going to reduce, come down a little, or come up a little relatively. And that is what is a minute, doctor is calling me.
Oh, sir, please, we can hear you. Are you talking, sir?
Yeah, gotten a call.
Sorry, sorry. I was on
Oh,
phone.
sorry. I didn't
I'm
know
having
this.
another practical session too with the level 100, so I got a call that they are looking for me. But anyways, sorry. Let's go on. So let's go to the last one. Someone should help me with the last one, I beg. Please, this is our tutorial, so I will not be setting a different question for us to go through. That is why after every session, I just bring some questions there so that we test our knowledge and see if we have an understanding everything. Is that okay? If there's a need
Okay,
for me
sir.
to set a question, but this is our tutorials for now. Is that okay?
All right. All right. Question 3. An electron in the conduction band has a higher energy than the electron in the valence band.
Okay. This is very straightforward. Is that okay? Because when it's at the valence band, it needs energy to go to the conduction band. So it means if it has a conduction band, of course, it will get or it has a lot of energy as compared to an electron at the valence band. Is that okay? The same way electrons at the valence band is going to have more energy than electron that is at the first shell or the second shell or something. Is that okay? Because if you remember Bohr's theory, Bohr was explaining that anytime an electron needs to move at a higher energy state, it needs energy to do that. Is that okay? So it means anytime it is high, it has more energy out there. Is that okay? And anytime it's low there, it means relatively it has low energy as compared to the one at the top there. Please, are we clear about this? Can we go on?
Hey, I'm not clear here. So meaning you said electrons, okay, and electrons in the conduction band has higher energy than electrons in the valence band.
And yes.
I'm not clear here. Looking at when you look at the diagram, the valence band, the middle we have the forbidden band or the energy gap. Then before you move to what do you call the conduction band. So why is it that? So why is it that? Why is it that the energy level in the conduction band is higher than that of the valence band?
Oh, okay. Can someone help me?
Okay,
Okay,
so I
sir.
cannot try. Yeah.
So, my brother, you see, when the electrons are the valence band, you see, their energy will be lower because they need more energy before they can cross the energy gap or
Forbidden.
they can move to forbidden, but before they can go to the conduction band. So if you are the conduction band, that means you have more energy because if you don't have more energy, you can't go there. Okay, so for you to move from the valence band to the conduction band, you need more energy. So the electrons at the conduction band have higher energy compared to the valence band, and the electrons at the valence band.
Can someone also come in with a different perspective?
Hello, sir.
Yes, sir.
Yeah, so that's what they have said. The electrons actually need for them to be moved from that band to the conduction band. It assumes that they have one way or the other been excited, either with some form of energy, can be thermal energy, like you said earlier, to be able to cross. Other than that, we will not experience the conduction that we are talking about. Yeah, I said that it only happens when an electron is able to jump a gap, that forbidden gap that we talk about. So once that thing happens, we believe that that electron may have been excited and gain some form of energy compared to those that are at lower energy levels. So indeed, they should have a higher energy. Thank you.
Okay, thank you very much. So we are all following and understanding one way or the other, which is good. So please, do you understand the explanations that has been stated so far?
Sir, I'm not confused though, sir. I believe you can come out again. I'm not getting it right.
Sir,
Why
may I
the
also
energy
come back?
band?
Yeah. So maybe let
So
me
bring
finalize
your
it so
view on
that.
that.
So, Sir Francis, the thing is, Every
May I
shell,
make my view? Okay.
every shell follows up to the other one. And if you remember, we have something we call the quantum number. Is that okay? The principal quantum number. Quantum number 1 is the first shell that is very close to the nucleus. Quantum number 2 follows up. Quantum number 3 follows up. And as it's going up there, the ability of an electron to stay there, it means has higher energy relative than the lower one. So an electron that is staying at the quantum number 2, of course, has higher energy. From Bohr, I'm not even talking about semiconductors. I'm talking about Bohr. Like I'm taking you back to atomic theory. Has more energy relative than the one that is at principal quantum number 1. The same way the one that has energy at principal quantum 3 is higher than that one for principal quantum number 2. And if an electron is at principal quantum number 2 and it wants to transit itself to principal quantum number 3, because that place the energy is high, it needs to get a form of energy one way or the other from any source. Of course, it can be thermal, as Bismarck said. It can be any form of a photon. It can be any form of a heat. Anything. Is that okay? So it's able to get enough energy to move itself from its state to a higher state as it wants. Is that okay? The same idea applies to a conduction band and a valence band. You know, we said the valence band is the very last shell that we are talking about. And the conduction band is a shell that follows up to the valence band. It means that it's higher than that of the valence band. And whatever being the case, if you want to transit yourself from that valence band to that conduction band, it means you need some form of energy to stay up there. Is that okay? So it means that if an electron is at the valence band and we have another electron at the conduction band, their energy is not going to be the same. One, of course, has more energy than the other one. Is that okay? So the one that is at the conduction band, of course, will have more energy than the one that is at the valence band. And if the one at the valence band wants to go to the conduction band, as we said earlier, it needs energy to go up there. Is that okay? So where they are, it's not the same. We are not the same. As we are here, we are not the same as the politicians and the MP. We have levels. Is that okay?
Understood, sir.
If we want to reach there, we need a different state to reach there or different energy to reach there. Is that okay? So maybe let's go on. I think our break time is almost.
Thank you, sir, for the clarification. Thank you very much.
Yeah, so let me chip in with this. I think I also heard you that in any case, if that energy is even removed at a point in time, the electron will drop back to the valence band. Is that correct?
Yes. From Bohr.
Yes. Yes. So the question, why is it dropping? It mean that energy has been lost. So it's coming down again.
And this one, what I'm
Hello.
explaining, it's yes.
Hello, sir. Hello, sir.
Yeah.
With such reaction, is it practically done with this type of the covalent bonding and the ionic bonding? I mean, the reactions. Is there any way you can practically do it or perform it?
Are you talking about the energy transitioning or the bonding in terms of the semiconductors?
Yes, sir. Yeah. The energy transition. I mean, the quantum jumps from one energy level to the other. Is it practically is it done?
So the lasers, the LEDs we are using, they are all due to these principles. There's an energy up there. You will apply energy in the form of, say, electricity to the material. It gets up there. It is not stable. It gets de-excited. So it comes down. In the form of coming down, it emits photons. Is that okay? That is why we have something like spontaneous and stimulated emission. It emits photons. And the photons that they emit is a form of the light that it gives us. So you will think you've gotten a bulb that is giving you light. But mechanically, that is what the principle that it's using there. Is that okay? And a very, very practical and a typical example is, you see, we have this rosary band, the one that the Catholics put on their neck. Is that okay? That one, if you are in darkness, you see it glow. You can give it light. Say you enter a sun, it will absorb a form of energy. When it absorbs, all the energy states goes very high. When you are in darkness, it's not very stable up there. It needs to come down. So in the form of, say, coming down, that is where it emits this kind of photons for you to see as light. Is that okay? And even we are even diving into more distance, we call it the phosphorescence and other things. Is that okay? Which that is not what we are doing anyways. But practically is very a typical example. Is that okay? The LEDs, the lasers, they are all typical examples of it.
Thank you very much, sir.
So Sir George, your hands is up. Should I go on or you have a question?
No, no. I'm saying that, are we going to continue or we'll take a 10 minutes break because the break is supposed to be at 9?
Okay. So maybe let's take about 10 minutes break to charge our phones. Is that okay? So it is 9:24. Maybe let's meet at 9:40. That would be too much. Okay, 9:40 will be like 15 break. So let's take 15 minutes break. It's fine. Is that okay?
Okay,
So we
sir.
meet here at 9:40 so that we charge our phones.
So by
Okay.
9:40, you should all be present.
9:40,
Okay.
I'm
Thank you,
starting
sir.
at 9. Do you all agree? I beg.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So meet. See you at 9:40. Hello, are you all back? Hello, our time is up. Where are the rest? Kindly inform them to join it for me, I beg. Is that okay? Please, those who are online, kindly inform the rest to join right now so that we start. Hello, can you hear me?
Bernard, why are you showing your video and eating our data?
Hello, are you back? 14.
Yes, sir.
Our number is not encouraging. The break taking, I think the best is to finish with everything that we take the break. When you take the break, we are coming back. It's another problem.
Sir, you let everybody, you made it aware that time we're returning. So this one, you shouldn't say that. Maybe I don't know, but that's my opinion. That since it is the time you gave is up, you continue. Maybe people have other things. People may be eating. Others may today is Saturday. Others people have a lot of things to do. So we can continue later. They join.
Okay, but anyways, kindly put it on a platform that I'm starting. If you have a common group, kindly put it on that platform for us. Okay, so now, let's look at something called the drift velocity, and this is quite simple, but let me just explain it to you. A little bit complicated. This is how this thing behaves. So you see, when electron is actually in any matter, say our solid, is that okay? It doesn't. Ideally, we may expect it to move into its after applying a particular electric field to it. Is that okay? So let's say it starts from here, it just goes straight where we want it to go, then that will be all. But ideally, that is not how it behaves. Is that okay? It behaves.
Sorry, sir. Please, Benjamin, mute your microphone. Benjamin.
Ideally, we may be expecting the electrons to just move at the straight end, then come back, but it doesn't behave that way. Is that okay? Before an electron will start moving from this end to the other end, it would have met so many obstacles one with the other. When I say obstacles, I mean collision. Is that okay? Colliding with its fellow electrons, colliding with other things, and that is it. And you can think about it like sending a child to go and buy you something. If the child has to just go straight to the store or the supermarket, go and get what you want and come back, it would have been very easy, save you a lot of time. But you send a child at 10 a.m. and the child is returning like 11 a.m. Is that okay? The child will use about 1 hour to go and get what you want and come back. Because when it's moving, he or she will see something on the floor, pick it up, see a friend, say hello to it, see something going on, stand and observe what is going on, And it's not a straight pattern that the child is going to use and go and get what you want and come back. The same way the electrons behave. If electron is in a material, it doesn't know the path it is going. Is that okay? So it can just be oscillating, be vibrating at its own pace. When we apply electric field, we expect it to move at a direction that we want and to a place that we want. Is that okay? And when it is doing that, we may think that it should just go straight and come back. But it will not behave like that. It will behave like the charge scenario I have just explained. It will collide with another electron, and because of the collision and the angle of collision, it will tune or influence the path that it will move next. Then it will collide again, it will collide. But at the end, it knows that I'm going to buy something. But before going to buy that thing, that is the collision and that is what is happening. Is that okay? And this thing can actually behave in a path that we can relate the force, the charge, and the electric field. Is that okay? And this is no new formula. This is very old. Is that okay? It's very old from electrostatics that we derive this. But we are just happy to derive something we call the drift velocity. In terms of drift velocity, we want to know the average velocities that this electron or this particular electron will cover before it reaches its final destination that we want. So after the collision, it will cover about a particular space. After another collision, it will cover about a particular space. After collision, it will cover about a particular space. So all the spaces is covering before it reaches the final destination. or final path where it has to go. That is the EM field applied. That path and all the average velocities, all the individual velocity, we average it, and that is what we call the drift velocity. Is that okay? And mathematically, we don't need to do a proof of this, but mathematically, we can relate drift velocity and the mobility and electric field. Is that okay? So we have the drift velocity to be proportional to of course, the electron mobility and the electric field. And the negative here represents the direction that is moving. You see, when electron is moving this path, we expect the electric field to move opposite to it. Is that okay? And that is what is bringing the negative attached to the electron mobility. And this is the electron mobility. This one. Is that okay? Let's use a laser pointer. So this is the electron mobility. This is the electric field. This is the drift velocity. And drift velocity is the individual velocities here that we've averaged. Is that okay? So the electron is here. We want it to go straight to this end. But to not do that, it will first go here, collide with one electron, it will influence the direction that it's moving, collide with another electron, influence the direction that it's moving, collide with another one. Is that okay? And it's not only this electron that is behaving that way. All the electrons that is in that material will behave that way. Is that okay? It's not just going to go straight to where we want it to go, but there will be a lot of collisions. Is that okay? A lot of collision before it reaches its final destination. Please, do we understand? Am I confusing you or you are good?
Yes.
The yes is for the confusion or the yes is for you are good?
It's for understanding.
We are good to go, sir.
Okay, great. So under drift velocity too, we can bring one terminology that we call it the mean free path. Is that okay? And the mean free path, we want to just find the distances, the average distances the electrons travel between each collision. Is that okay? And as I told you earlier, the electron will start moving, it will collide, influence the movement. But at the end of the day, the electron knows where it's going. It knows that those who are in Cape Coast here, it will know that I'm starting from Peru Junction, I'm going to Abra. But because, and it's even like we are in the market, like Makola or those who are at Kumasi, like KGTI market. You enter into a market, you know your exit. But the exit is not a straight path there because a lot of people are there. Is that okay? So you have to dodge from one path, enter one end, collide with someone, the place is choked. So you have to move from a different path and go and find somewhere, and that, but at the end, you know where you are going. You know that you have to exit the market. Is that okay? And that is what is going on there. And that velocity is what we are terming as what? The drift velocity. Now we have something again we call the mean free path. The individual distances that is covers. Is that okay? So it starts moving. You start moving in the market. You bump into someone. You've covered one distance. After bumping into someone, you bump into another person. You've covered another distance. After that, you've bumped into another person. You've covered another distance. That's distances that you've covered. Is that okay? That's short distances. The average of all these distances is what we call the free mean path. The mean free path. Is that okay? And this path is actually influenced by temperature a lot. At lower temperature, the mean free path is different from at higher temperature. Is that okay? And when say we are at low temperature, like in the market, everyone is very stable. But suppose we are in the market and it starts raining, everyone will start to look for shades, start packing his stuffs or her stuffs from the ground and everything. Is that okay? And it's creating a lot of chaos. So when you do that, your distance and your path will actually increase because this time around, maybe there will be a little space for you to move up and down. But this time around, everyone is moving. You just make one step and someone is there. You make another step, someone is there. You make another step, someone is hitting you. You make another step, someone is pushing you. Is that okay? And you are just pumping on other people one way or the other as you are moving. And that is what we are saying the temperature has increased in the material. So when temperature increases in the material, the vibration of these molecules of these electrons increases a lot. Is that okay? It's actually increasing a lot. And as it is increasing, and the electron knows the path that is supposed to cover to that end, it's not going to take it easy. Is that okay? Because it moves more, it will chance on another electron and collide with it. It moves more, chance on another electron and collide with it. It moves more, chance on another electron and collide with it. Exactly. So we are saying that anytime there's an increase in temperature, the mean free path of that particular material tend to what? Reduce. Is that okay? Because this time around, you are not getting a lot of space to take about 2 steps or 3 steps. You make a half step, you meet someone. You make another half step, you meet someone. You make another half step, you meet someone. Unlike lower temperature, the electrons are a little bit stable. Is that okay? The vibration, of course, is very less. So at least you get a chance to be moving compared to when it's at high temperature. Please, do we understand?
Yes, please.
It's a build up, so we have to understand it so that we can move on. Okay. So now this thing will actually influence the drift velocity a lot. Is that okay? So at the end, if we have the mean free path decreasing at high temperature, we expect that the drift velocity should also what? Decrease in that perspective. Is that okay? And of course, there will also be a decrease in electron mobility. The electron movement will also decrease. Is that okay? Because if the distance is covering is small, of course, the velocity too is also going to be small. And of course, the electron mobility too is also going to be small. Is that okay? So temperature actually influences the movement of an electron. Apart from it giving it energy to move, transit, and other things, it actually influences the movement of electrons a lot. Is that okay? And as time goes on, I'll bring this thing up, then we'll discuss more. Now, our understanding that we've gotten from the drift velocity, the mean free path, their respective relation in terms of temperature, in terms of also electromobility, in terms of also drift velocity. Let's put that understanding there. I'll come back to it one way or the other. Is that okay? So let's put this one there. Now, it looks like something like a semiconductor. And as I said earlier, if you're talking about intrinsic semiconductor, we are talking about the pure state. Is that okay? And at absolute temperature, like 0 Kelvin or negative 273 degrees Celsius, we expect that there's no electron at all. Is that okay? All of them are stacked. And we are saying we have our intrinsic semiconductor. So if all the electrons are stacked, of course, it's behaving as what? As insulator. There's no current going through, there's no absorption, whatever being the case. And of course, no other physical processes of interest. Nothing is going on. Now, if we tend to increase the temperature in an intrinsic semiconductor, we are talking about intrinsic semiconductor. Interestingly, the temperature will be able to elevate some of the electrons that we have in there. Is that okay? It can eject them. So, in as much as it's a semiconductor, this time around, it can let electric current flow through it. And of course, we can see that if it's behaving as a conductor, it has, of course, high energy state. And if it's behaving as an insulator, of course, it has a what? Low energy state. Is that okay? And this time around, we cannot say the electron cannot attain energy values intermediate of these two levels. Like we don't have different levels between these two of them because it's just a semiconductor that we are talking about at a high energy state and a low energy state. Is that okay? So we take a pure semiconductor like an intrinsic one, and we are saying that if no temperature is at all applied, like 0 Kelvin, is that okay? At absolute temperature, we expect it to behave as an insulator. But if we give it a room temperature, exactly, a temperature above absolute, we expect it to behave as a conductor. And if it's behaving as a conductor, we are saying that it has high energy state. And if it's behaving as an insulator, we are saying it has a low energy state. Am I confusing the class?
No, sir.
So can we go on?
Yes, please.
So I think the class will be ending at 11, right?
Yes,
Yes,
sir.
please.
So I think we can finish up, hopefully. Now let's look at something here. Now, I mentioned the fact that we can do something like doping, where instead of the intrinsic, we don't want it the intrinsic, we want it the what? Extrinsic. And here we apply some impurity to that intrinsic semiconductor. And when you do that, we have two ways of doing that. We have the N-type semiconductor or the what? P-type semiconductor. And what the N-type semiconductor is doing is we want to produce by adding a donor impurity. Is that okay? And when you say a donor impurity, we want to increase the number of what? Electrons in there. So if that is the case, it means we have to try and bring in an electron as an impurity. So an element as an impurity, but this time around, the element has more electrons. When I say it has more electrons, relatively, you see the bonding, we need valence electrons of 4. Is that okay? So if you're able to introduce an element that has valence electron of say 5, it means we are bringing an impurity that is also serving as giving us one extra electron as an SS. Is that okay? And this time around, this type of a semiconductor, we call it a what? N-type semiconductor. Is that okay? And the doping can be in different elements. As far as the valence electrons of this particular element is 5, we are good to go. And a very typical example is the phosphorus. What element is this and what element is this? Hello,
Arsenic
am I
and
on?
antimony.
Yes. The first element is what? P means what?
Phosphorus.
Phosphorus. AS means what?
Arsenic.
Arsenic.
Okay. And SB means what? Come again. So someone mentioned it earlier. I said
Antimony.
SB.
Antimony. SB. Antimony. 51. Atomic number 51.
Come again.
Antimony. So antimony. Atomic
Okay.
number 51 or so. Something like that. Antimony.
So thank you. So at the end of the day, we need an electron, an element that has an SS electron of say 5. Is that okay? And now this is how it's going to behave. Now we expect, if you remember, the previous structure that we do, we're having silicon, and this time around we are just doping it with 1 per millions of it. So we bring only one phosphorus. We can bring the phosphorus, we can bring the antimony, we can bring the which element again did I even show here? Arsenic. Okay. We can bring the arsenic there. Is that okay? So any of them that we bring, as far as we have the valence electron to be 5, we are good. So the 4 of them is going to bond, of course, with the neighboring silicon. Is that okay? And again, we will be left with what? An extra electron here. So the phosphorus came with a valence electron of 5. So 1, 2, 3, 4, 5. And the 5th one is the extra one that is sitting here. Is that okay? The other 4 bonds with the what? The neighboring of the silicon. It'll be very strong. Is that okay? So that it will have a good structure. Now, when we are done, we want to know what will happen if we apply a current through this kind of a semiconductor. And again, this type of a semiconductor is called what? N-type semiconductor. Now let's look at something like this. Let's look at the schematic that I have here. So I have a battery and I have my polarity, that is the positive and the negative. And of course, I'm expecting the conventional current to pass through, that is the positive to the negative side. But this time around, I have S6 electrons there. And I'm expecting that anytime the material is actually moving with the electron, and when you are talking about the movement of electron, it's directly, it's opposite the movement of that of the current. So as we apply the current, we expect that the conventional current, we expect that our electrons to be moving in the opposite direction. But here, the movement of this opposite direction, the SS is electrons. It's electrons that is doing this kind of a movement. Is that okay? And of course, we don't expect the holes to be more here. Of course, the electrons will just transit to another one. It will create a hole here. Another electron will come and fill that hole. The one behind will create a hole. Another electron will come and fill it. Is that okay? And at the end of the day, we get electrons in that particular type of a semiconductor. Is that okay? And now, this time around, we have decreased the number of holes in the N-type semiconductor as compared to that of the intrinsic semiconductor. And if you remember, I told you that intrinsic semiconductor, if we apply heat or EM flow to it, we can tend to let it behave like a conductor. That is where it has high energy level. Is that okay? But here, we've created extra electron and we have applied EM flow to it. Is that okay? So the movement of electron, the decrement of a hole is not the same as an intrinsic. Is that okay? It's going to be different because this is an extrinsic semiconductor. Is that okay? It's going to conduct more than that of than the intrinsic that we applied energy to it. Another type 2 is called the P-type semiconductor. And this time around, the first one, opposite of the first one, instead of making excess of electrons, here we are making excess of what? Of holes. And it's very easy here. Now we have a particular semiconductor, and that is intrinsic semiconductor. And we want to do a bonding, we want to add an impurity. But because we want to create a hole, this time around, we don't want excess electron. We don't want more electron to be given. So we will just have to get an element that has a valence electron of 3. So, and when it's bonding, we are expecting 4 valence electron to bond with the neighboring to create a very strong bond. Is that okay? Like the covalent bond. But it's not behaving that way. We need only what? Only 3 electrons at the valence shell. It's very important. Now, when we get the 3, 1 bond with the neighboring, 1 bond with the neighboring, 1 bond with the neighboring, it will be left to the last one to bond. And that one, it has no electron. And in that sense, it creates what? Something called the dark hole. Is that okay? And now a very typical example of this kind of an element is the B. B represents what?
The boron.
Boron. And GE represents what?
Gallium.
Come again.
Gallium.
The indium is the IN, is the last one. Now, this is how it's behaving. I'm using a boron. I have a silicon sitting here, silicon. It is doing very well. Now, I take the boron, I add it as an impurity. Now, 1 bond here to make it this end very stable. Another valence electron here, another valence electron here. It bonds to make it very stable. Another valence here, another valence. It bonds to make it stable here. But interestingly, it reaches here and the boron has nothing to offer. It's only the silicon that has its electrons sitting here. Is that okay? And this is what creates the hole. Is that okay? So still it's lacking. Is that okay? And here we are seeing that the majority carrier is the hole. Now let's look at how the EM field is going to be related to this kind of a material. Now, if we have this kind of a material, you may expect that the electrons too may dominate. No, it doesn't work that way. It's the hole that is going to dominate. and we still have our conventional currents going this way. But because the holes are more than the electrons moves from one hole to the other one, create another hole as usual behind, and another electron can fill that path, create another hole as usual behind. Is that okay? So now there are a lot of sitting holes in front and beside, where the electron can just be jumping on and be moving. Is that okay? Because of course we've applied an electric field to it. Is that okay? And this one tends to cause the electrons to flow in this type. Is that okay? Now please, do we understand the N type and the P type? Any questions so far? Any questions so far?
Hello, sir.
Yes, sir.
Please, concerning the P-type semiconductor, may I know the difference? Is it one sends a donor and the other one sends a acceptor, or which is it? Can you help me with the difference?
Yes. So one is serving as a donor, one is serving as an acceptor. The P-type is serving as an acceptor. Is that okay? When you see an acceptor in purity, it's ready to accept another electron, of course. And when you say a donor in purity, it has access to donate one. Is that okay? And when you look at the P-type semiconductor, please mute yourself. Okay. Please, let's be careful about this microphone. Some sensitive stuff, we have to be careful. Okay.
Hello, sir.
Yes, sir.
Please, so whether it is a P-type or N-type, the ultimate aim of doing it is to transfer electron from one atom to the other, so that it will cause the movement of electricity, isn't it?
Let me shape it. What you said is correct. Let me shape it to it. The main aim of doing this is to increase the conductivity of the material, to cause electrons to flow in the material. Is that okay? Now we have a pure semiconductor. And a pure semiconductor, we call it intrinsic semiconductor. The only way that kind of a semiconductor can cause an electron to move is when it gets energy like temperature, as I showed earlier in this slide. Is that okay? This is a very pure one, intrinsic one. We've not doped it. It will get some of the energy to remove some of the electrons, and it will cause electron hole pair movement there. It will behave as a conductor, but not a pure conductor, just a normal conductor, because we have some electrons to be moving there. If nothing at all, no energy at all, no heat at all, it will behave as an insulator. Now, we are not interested in this one. We want to find a ways of causing more electrons in the material to cause more movement of these electrons. And that is why we dope them. We dope them either increasing the number of electrons or increasing the number of holes. Is that okay? But again, our main motive, again, is to be able to influence the movement of electrons in the material. If electrons move in the material, it means it can conduct. And that is what we want. Is that okay?
Yes.
So we are controlling that movement to fit what we want to do. And that is what I'm saying, that we have two types of these materials. We can either add excess electron, or as the material is, find a material to put in there, and it will be lacking one electron in there. And because it's lacking one electron in there, electron will tend to be filling the port that it has been lacked. And as a result of that, the electrons will be moving in the material. Is that okay? And because, yes, sir.
Sir, I want to ask this question so that it's very clear. The excess electron that we have produced of holes, in terms of energy level, are they found in a new energy level compared to the valence electron in the existing atom?
Please come and give me the question, I beg.
I'm asking that for this excess electron, we either holes or electron that are created after doping. Those excess electrons, are they found in a new or higher energy level compared to the bonding ones? Just want to understand that one.
Oh, okay. So no, they are not found in any other level as we are talking about. Of course, we have our
Okay.
valence band and we have the conduction band. Is that okay?
Mm-hmm.
But we want to look at how these electrons moves around. Is that okay? And now their movement is not pertaining to their conduction band or the forbidden band. The movement is pertaining to it moving and occupying another hole. When I say another hole, the electron moves, it creates a hole behind. Another electron see that there's a hole behind. Because there's EM field, energy enough to move, moving, it will come and occupy that hole again. And that is what it will be doing. Is that okay? And as a matter of it moving and occupying these holes, it will cause its conductivity to be high, one way or the other. Is that okay?
Oh, okay. Okay. Thank you.
You're welcome. So now, if we understand these two, let's look at something here. Something we call the mass action law. The mass action law is very important. Yes.
Sir, question. In regards
please
to
do.
the N type, regarding the N type and the P type, I'm talking about the N type, P type semiconductor. Is it necessary? I mean, must it be necessary to always use a semiconductor atom or element in that process?
Okay.
I'm asking because for the P type, oh please, I'm coming. For the P, for the N type first one, but you said, I mean, it can only be produced when there is what a donation. When there is a donating of, let's say, some of the atoms like the phosphorus, antimony, and what have you. But looking at this one, looking at the P type, a boron was used, and I was asking myself, is a boron a semiconductor? You use boron and gallium. Hello?
Yes, I'm listening.
Hello?
Yeah, hello.
You use, what do you call, a boron. So I wanted to find out, is a boron a semiconductor?
A boron doesn't fall under semiconductor. From my explanation that I made pertaining to semiconductors and the valence electrons around it, what do you think a boron will be? A boron has valence electrons of 3.
3. Hello? Bad network.
I'm having a class, so hopefully by 11, 12, I should be done. So be expecting me around 12. I beg. I should have given you a prior notice. Yeah. So can you hang around till maybe 11:30, 12 there? I beg.
Sir, the class closes at 11:10.
Okay. Yes. Today I didn't go to the lab. I'm in the house doing the meeting. So maybe by the time I get there to be at 12. So the question is, you are asking a very nice question. The question is, look at this particular element. Boron has 1, 2, 3. How many electrons, valence electrons does it have here? Ibrahim, it was Ibrahim who was 3. Very good. So it will fall under which kind of a material? A conductor, some conductor, or some an insulator. What do you think?
Semiconductor.
No, look at it well. Can someone help me here?
Sir,
So the
looking
question
at the
again.
various elections there, I think it should be based on the rules that, I mean, when you look at the electronic configuration, once they're saying that group 1, group 2, group 3 elements, they are metals, and metals are conductors. So, from my point of view, I was thinking boron should have been a conductor instead of, let's say, semiconductor or insulator.
So boron is a conductor. That is what you are trying to say. So it's not a semiconductor.
Yes, please.
A boron is a conductor because of the valence electron. It's 3. Is that okay? So at the end, it will tend to move at the conduction band and other things. But pertaining to a semiconductor studies and impurity addition, we are not considering a boron itself as a conductor or a semiconductor or an insulator. We are considering it as adding one of them to millions of a semiconductor and creating either excess holes or excess electrons. Is that okay? But
So
because right now we've seen that if we get excess electrons and excess holes, we can actually have an influence on how the material conductivity is going to behave. Is that okay? So I have a semiconductor. I want it to be conductive, but I want to control its conductivity path. I want to control how it will be conductive. Is that okay? So I'm just adding an impurity of an interest. I know that when I add this amount of impurity, I get this amount of free electrons that is going to move, and I get that my desired results of a conductivity. Is that okay? So now it's not a single subject element of study of its conductivity or insulator. We are considering all of them again, and we are considering how we are going to make excess electrons and excess holes in this kind of a material, like a whole semiconductor. Ibrahim, do you get? Are you following this? Is Ibrahim online?
Yes, please. I'm online.
Are you following?
Yes, please, sir.
So that is what we are trying to do. We are just trying to see how we can control a material conductivity, because at the end of the day, we know that if you have a semiconductor, it has this particular property, but with some conditions, it can be an insulator. With some conditions, it can be a conductor. And even if it's a conductor, how conductive it is, how do we make it a conductor? Is that okay? Do I introduce an amount of electrons or do I introduce an amount of holes to get that kind of a conductor? Is that okay? Yes, Dixon. Hello.
Yes.
Sir Rabi.
I want to ask, why are engineers, what about the purpose of doping is to increase their conductivity, right? Yes. And we have conductors there. Why are they bent on these semiconductors? There should be a physics behind it. Going ahead to dope it to improve its conductivity. Why they should have gone for conductors?
Yes. Service Mark, you are on point. But again, the thing is not about the conductivity, it's about controlling the conductivity.
Okay.
Is that okay? It's not about we want a conductor, so we bring in a material, because already we know the conductivity of a conductor. Is that okay? But we want a semiconductor that we can control the amount of electron movement in the material. We can control how conductive it should be. We can control how insulative it should be. Is that okay? That is what we are dealing with here. Is that okay? So it's not
the
straight
factor
to the
is
conductor.
ability to control the flow of the electrons.
Very good. Now that is what we are
That
doing.
reminds me, because I'm asked this question because of this. We also know what are ohmic conductors and non-ohmic conductors. How do we put in that coming to this aspect? What do we mean by ohmic conductors and then non-ohmic conductors?
I'll explain this one. I have it in the subsequent slides. If we are able to finish up, I think it will come up. It will surface one with that.
Okay.
If we are not,
All right.
we will see it in our session.
Okay. All right. Thank you.
I think it should be in.
Okay.
Okay. So please, can I move on?
Yes, please.
So now let's look at one important law under semiconductors, and we call it mass action law. It's very, very important because what mass action law is doing is, if we have a semiconductor, whether intrinsic or extrinsic, we want to know the material's concentration of electrons and holes in there. Is that okay? Because we expect that if the material has an electrons, it has a holes, we expect all the two of them should be equal to the concentration of course, the electron and holes in that particular intrinsic semiconductor. Is that okay? So the formula for mass action law is very simple. It's just N multiplying P times of course, the intrinsic carrier concentration. And here we are talking about the concentration of holes or the electrons in the intrinsic semiconductor. And the N here is purposely telling us the concentration of electrons in the semiconductor. And this one is telling us the concentration of the P is telling us the concentration of holes in the semiconductor. Is that okay? And the Ni here is telling us the concentration of the holes and the electrons in that particular semiconductor. Is that okay? So we expect it to be equal, ideally. If I take the concentration of holes, concentration of electrons, I expect it to be, of course, equal to the concentration of holes or electrons that I have in the semiconductor. But this formula actually varies depending on the material. Depending on the material like N-type semiconductor, it will vary. Depending on the material like P-type semiconductor, it will vary. Now let's look at this. If I have a material like any material at all, I'm expecting the electrical neutrality to be equal to, say, the proton should be equal to the same as the electrons. Is that okay? So the number of negative charges should be equal to the number of what? Positive charges. Or since we are dealing with electrons and holes, I'm expecting the number of holes should be equal to the number of what? Electrons. Now, ideally, if I have the number of holes, the number of electrons, I'm expecting that the number of electrons should be plus of the what? The number of bound acceptor atoms. When you say bound acceptor atoms, the ability of these electrons able to accept more electrons one way or the other. Is that okay? And the same way, I'm expecting that the number of holes should be plus of what? The number of bound donor atoms. Now, if we are talking about electrical neutrality, I'm expecting the number of electrons at the top here should be equal to the number of what? Holes at the down here, ideally. And it's supposed to be something like this. Is that okay? For semiconductor to be electrically neutral. When you say neutral, we having the number of holes should be equal to the number of what? Electrons. They should be equal. So if that is the case, I have my bound acceptor plus the electrons. I have my holes plus the what? The bound donor. Now, let's look at the individual semiconductors. When I say individual semiconductors, I mean the P-type semiconductor and N-type semiconductor. Now, when you're talking about N-type semiconductor, we are not accepting one way or the other any electrons of that as such, because already we have excess electrons. And for N-type semiconductors again, our number of holes is less than the number of electrons, the concentration. The concentration, we expect the concentration of electrons should be way higher than the concentration of holes. So if that is the case, it means it will change the neutrality formula that we have, the one I showed you before. And at the end of the day, instead of getting my N plus, say the Na, now the Na goes to 0. My P plus the Nd, now the P is going to go to 0 because I'm expecting the concentration of the electron should be equal to the concentration of the what? Of the holes. So at the end, I'm going to get N to be equal to what? Nd. That small letter n to be equal to what? Capital N what? D. And here is my what? My bound what? Donor atom. Now let's look at the mass action law. Mass action law gives us this. And now since we have N to be approximately equals to the ND, we can just substitute where the N is with the ND. Is that okay? And when you put the ND in here, we make the P the subject, we are going to get what? Ni squared, still the concentration that we want, divided by the what? The ND. That is derived from the N. Please, are you following? So for a mass action law, under N-type semiconductor, we can calculate the what? The concentration of what? Of holes as what? N squared divided by what? The NB. Please, I'm moving on. Should I?
Yes, sir.
Now, if we want to also consider the different type of a p-type and different type of a semiconductor, that is a p-type semiconductor, it's the same situation that is going to happen anyways, because this time around we are not accepting any donor, so our donor go to 0, and of course we expect the concentration of holes in p-type semiconductor to be more than the concentration of what? Electrons. So now the neutrality formula is going to change. Now ND is 0, ND was here, it is 0. The N plus Na here, this time around, because the concentration of holes is more than the concentration of electrons, this one too can go off. And again, we will get our P to be approximately what? Na, the bound acceptor atom. Now let's bring the mass action law in here. Mass action law is saying N dot P equals what? N squared. If I have N here, now my P here has changed. The P here this time around is Na. That is capital Na. Is that okay? That is the bound atom acceptor. We can put that one here. We make N the subject, and of course, we can just do change of subject. The Na is here, it will come and divide what is here. Then we get N squared divided by what? Na. And that is all. So you see, the mass action law works differently under the different type of a semiconductor. And anytime you are given a question, you have to read and know the type of semiconductor, unless maybe it's stated in the question. Know the type of semiconductor and know the formula you're going to use for this kind of a situation. Like, so here, I've done a summary of everything here. And now if we expect, if we are expecting, say, the N-type semiconductor, of course, the majority is carrier is what? Electrons. The minority carrier is what? Holes. And we expect the approximate concentration of the holes to be equal to what? Nd. And of course, of the electrons to be equal to what? Nd. And now we can find the concentration of holes of interest in the semiconductor, that is the N-type. Now the P-type to behave the same way. Our majority is holes, our minority is electrons. We can find the concentration in the semiconductor, that is the P-type, if we have this formula through the mass action law. So this is a very wonderful work that was done there. Any questions so far?
No, sir.
So, why our interest in the concentration of holes in an N-type material and then electrons in a P-type material? Because I think in either case, the holes are not the majority carriers. Why our interest in it? So,
Yeah, hello.
Yes, hello, sir.
Sorry.
So let's go.
I can see some chemistry magic going on in the group. That's great. Someone was about asking a question.
Yes, yes. So I was asking a question that in an N-type semiconductor, I look as if determination of the concentration of holes is of concern. Why not the concentration of rather the electrons, but rather they are focusing on holes in an N-type material. Similarly, in a P-type, they also want to determine the concentration of electrons instead of holes. And I'm finding out, is there any reason for that? Please.
Hello.
Yes, sir, please, we can hear you.
Service Mark, I can't hear you. Is it my network or yours?
Yes, sir. Yes. I think yes. I want to know if you look at the N-type, we are trying to determine the concentration of holes, and instead of maybe electrons. Then if you come to the P-type too, we are trying to determine the concentration of electrons instead of holes. Why that? Using the mass action law. And what would that be? The importance of that?
Yes. Okay.
I ask this because for the N-type, yes, the N-type, the electrons are the majority carriers, right? So I was thinking that maybe we'll be focusing on the So I want to know if there's a reason for that.
So when we have N-type or P-type semiconductor, whatever being the case, it's easy for us to find the concentration of, say, the electrons for the N-type. It's easy for us to find the concentration of holes in the P-type, just using the mass action law straight away.
Okay.
You can use this one, then you get it. That is all. Is that okay?
Okay.
But we want to also consider the fact that there's some acceptor atoms there, and there's a donor atom there in terms of doping. Is that okay?
Okay.
And after doping it, what influences the minority carriers? What is the concentration of the minority carriers again? Majority and the minority carriers. That is the most important. But if you have a pure state, or say just the N-type, you could have just find it here without considering the impurities at all. Is that okay? But this time around, we are considering one, the acceptor atom, and we are considering the donor atom. Is that okay? We are not considering its neutrality again. We are not considering the intrinsic semiconductor again. We are considering after doping what happens. And then after doping, someone will say yes, we've doped, but in the N-type we are interested in the number of electrons. But the number of electrons can just be defined or be calculated with the mass action law straight away. But here we are considering the impurities we added. This one, the ND. And after adding the impurities, what influenced the minority carriers? Is that okay? And here our minority carrier is the whole. Is that okay? And the same as the P-type. After doping, what influences the majority carriers? Is that okay? And here our minority again is the what? Is the electrons. So that is how the two of them works. We are stepping out of the bound of the neutrality, and we are considering one carrier more than the other one.
Okay. Can we also say that after determining the two values, you are able to ascertain exactly which are the majority or which are the minority carriers established?
Oh, of course.
From theory.
Yes.
Yeah.
So, but most of the times when the question is given, the question will state particularly that is
Okay.
N-type and P-type. And if you know N-type and P-type, we can, of course, know the minority and the majority carrier. And that will influence the formula that we are going to use. Is that okay?
Okay.
So right
I
from
mean from theory. I mean from theory, you are able to establish that indeed in the N type, the majority carriers are because you are determining the concentration of both protons and then
the
electrons.
host,
Is that not?
no, host and electrons. Let's go.
Yeah, host and electron in both cases. Yes.
Mhm.
So if you can use, for instance, the N type, you say you can use the mass action law directly to determine the concentration of the electrons in an N type. Then if you use
For intrinsic rather.
yes for rather intrinsic, for rather intrinsic. Okay, okay, all right,
So
okay.
if it's
So
intrinsic, that would be easier to
mhm,
do that. Is that okay? So when it's
okay,
extrinsic, that is what we use these formulas.
okay,
Mm-hmm.
okay. Then how do
So,
you
but
determine
because
the? Okay, that's okay.
how do you
When we now
determine
have
what?
the concentration of electrons in an N type
I have a
from theory.
typical question that we'll look at. I think it's at the next slide.
All right, okay.
Mm. Maybe let me just slide into that. So let's consider a silicon PN junction at a temperature of 300 Kelvin, and the concentration of it is actually 1.5 times 10 to the power negative 10 per centimeter. The N-type doping is 1.5 times 10 to the power 10 inverse centimeter or per centimeter. Now, let's calculate the concentration of holes for this particular material. Please, can we try this one up? Hello, class. Are we there?
Yes, sir.
Can
Say
we
we
try
are
this
here.
now? When I put question, then everyone is silent. Can we try?
Yes, sir, we are trying.
Yes, sir.
Okay, so just 5 minutes, I beg. Please, what are we getting?
Okay. 1.5. So I got
Times 10 to the
1.5.
power
10.
1.5 times 10 to the power 10.
Yeah.
Okay. Any different answer?
Yeah, the same answer.
Okay. I can see Mavis. Madam Mavis, please, what did you get?
Oh, sorry, it's actually Koju, but my phone was disturbing me, so I used to use my phone. I also got 1.5 times 10 to the power 10.
What was your unit, I beg?
Per centimeter.
Per centimeter. Madam Felicia, please, what did you get? Is Madam Felicia there? Okay, so can someone help me how we went through? How did you go through? How did you get a 1.5 times 10 to the power 10?
Okay, so let me try. Yeah, we have established that in an N-type semiconductor, the electron concentration is approximately equal to the donor doping concentration. So that small n technical is equal to capital ND from the question, which is about 1.5 times 10 exponent 10 per cubic centimeters. So by effect, using the mass action law, we can actually substitute for N over there for ND. So we can have ND dot P equals to N squared. So if you make the P the subject, you would have N squared all divided by ND. So if you put in the values correctly and you solve, you'll be getting 1.5 times 10 exponent 10, say.
Okay. So thank you very much. So this is quite easy and straightforward.
Thank you.
Yes. You see, we are giving the concentration of the material itself.
Yes.
Is that okay?
Yes.
And we are saying the
Yes,
material
sir.
concentration is 1.5 times 10 to the power 10. And that is
10,
for a
yes, sir.
treated semiconductor. Now,
Yeah.
if we are talking about N-type semiconductor, of course, we are interested in the holes, the minority carriers. And there's a
Yes,
formula
sir.
for that. And we've been given the doping concentration. Is that okay? As
Yeah.
1.5 times raised to the power negative, raised to the power 10 again. So the only thing that we have to do is to square this one and divide it by this. Is that okay? Because at the end of the day, this is our donor atom. And at the end, this is the concentration of what? The intrinsic material itself. So we are going to square this and we divide by this. And the formula is just here. This formula is what we are going to use. So you bring the first one, 1.5 times 10 to the power 10 here, and you bring in another one here. Then we are good to go. Any questions so far? Okay. So no questions.
If you get time, yeah.
Yep.
Yes, if you get maybe another, maybe at another time, you go back and look at the conducting action of N-type and P-type when they are forward bias.
Yes, we can look at that one. We will look at that one with time. So I think it's still in the slide. Now let's look at something. I want us to discuss a very simple thing here. Something we call drift current. And again, I told you that we have something called drift velocity. we have something again we call the drift current. And the drift current is quite easy. We are just interested in the movement of these carriers. Is that okay? In an electric field. So when we apply an electric field, of course, the holes or the electrons, they do move. But drift current is interested in their movement. Is that okay? So in the presence of the electric field, we expect the electrons will move in the net direction opposite of that electric field. And of course, we expect that the holes in the net direction of the what? Of the electric field. So if we apply electric field, we expect that the direction of the movement of the electric field should be opposite of that of the electrons. But for the holes, it should be the same. Where the electric field is going, that is where the holes will go. Is that okay? But where the electric field is going, it will be opposite of that of the what? The electrons. Is that okay? Now, we have something again that we call conductivity. And this is very important. And when we're talking about conductivity, of course, we are relating the current density, the charge, and the electric field. And they are all related one way or the other. I don't know if I should even give this one as an assignment. But let's hold on. Maybe let me just go through. Now, if you have a formula like this, there's one formula that I asked earlier, where I said we have a relation between R to be equals to the rho, that is resistivity. Is it going to be A over L or L over A?
A over L.
A over
L
L.
over A. L over
A
L over
over
A.
L.
It's L over A.
L over A.
It's L over
Let's
A.
be correct about this, I beg.
If
L over
resistance
A.
is the subject, then it should be L over A.
Okay. So if we have this, and we know that, of course, Ohm's law is V equals what?
IR.
IR.
Very good. Now let's look at this very careful. There's another formula as current density, where current density is actually related to 1, the current and the area across. Is that okay? And now we can define it as what? I divided by what? A. And I think this formula, I've shown it before when we were doing physics 102 over A. And there's another formula too that relates electric field. And now the electric field that relates is to the potential difference in the length. L. Now let's look at these 4 formulas. We want to derive the formula that is given beneath here. This formula. We are interested in this formula now. Now when you look at this thing very, very well, now the R that we have here, we can actually eliminate it, then bring V over I here. And of course, it will be equals to what? We know
Rho.
that rho, maybe instead of the rho, can we bring conductivity in? We know rho, let me bring a last formula here. Rho is always equal to what? The inverse of the conductivity, right?
Yes, sir.
So we can just bring 1 over conductivity, multiplying the what? The L over what? Over A. Now let's examine this very well. I want to actually find a way to bring in the current density, that is the J, and the electric field, that is the E. Now, do you know what I'm going to do? I will multiply both sides here by 1 over L. And multiply both sides, this side too by 1 over L. And of course, this L will cancel this L.
Cancel the I.
Then I can multiply this N2 by I. And multiply this N2 by I. Then when I do that, this I will cancel this I. Now let's look at the terms that is left at the left side and the one that is left at the right side. How many terms do I have here on the left side?
2.
Okay, so it's which one? V over what?
L.
V over L, perfect. And the right side is what?
1 over resistivity A.
1
over
resistivity. No, conductivity, sorry.
A.
No, this is conductivity.
Conductivity. Okay, conductivity A.
The A is a denominator, but this I here is okay. So it's I over A rather. Okay, so we are almost there. Now the V over L, it represents the electric field, the V over L. So we can just write our electric field representative here. Then of course, we have our 1 over the conductivity. The I over A represent the what? The current density. So we can just write our current density J here. Now, we are interested in making the J the subject, the current density. So what we will do is to just multiply the conductivity to the other side here. Is that okay? So that we get conductivity multiplying the what? The E. Please, do we get it?
Yes, sir. No, sir. Please, can you go over again?
Okay. We are using about 3 terms here. So we have 1 term here. We have another term here. We have another term here. We have another term here. And we have another term here. Please a minute. Okay, sorry, please. So look at the terms here. You are familiar with this term? You are familiar with this term? If I remember, during the electricity section in physics 102, I taught this, and I also brought this thing up. So if you are not familiar, I've brought it again. Is that okay? So we have this term that we want to just do some changes to it. But the most importantly, we are using this term rather. Is that okay? R equals the resistivity multiplying the length divided by area. Now when you look at this one, this particular formula, we can remove the R, make R the subject here to be V over I, and come and replace it here. And that is what we did here. Is that okay? The next thing that we are going to do is, after getting this, we are not interested in what is beneath here, because we want to bring in current density and we want to bring in what? The electric field. Is that okay? Now, what is going to go on here is, since we have V over I, and what is of interest is V over L, but we have the L here. So we multiply both sides by 1 over L, so that at the end, the L here will be slashed out. Then I will be left with L here. Is that okay? That is why I have V over L in this term here, on the right side of the equation. Now again, I'm not interested in the I here, but I want the I at the other side. So I'll multiply both sides by I. So we cancel each other. Then there will be I over A. And you know, rho, that is the resistivity, is inversely proportional to conductivity. So instead of bringing the resistivity, you can just remove it and replace it with the conductivity. Is that okay? And at the end of the day, we can get something like 1 over the conductivity, the I divided by the what? The A. Is that okay? Now when you have V over L, you have I over A here. We know perfectly that the I over A can represent the what? The current density. And the same way, we know perfectly that the V over L can of course represent the electric field. Is that okay? So we just put in that. Then we get E equals 1 over the what? Conductivity multiplying the what? The J. And now, because we want to make J the subject, of course, this one we just multiply what we have here, and we get what? Current density equals conductivity multiplying the what? The E. And that is what we have here. Is that okay? So we have our current density to be equal to what? The conductivity multiplying the what? The electric field. And it's very important we know that. And here, our conductivity is related as this whole term here. This whole term. We have N multiplying the mobility, P multiplying the mobility. And the mobility we are talking about here is the mobility of electrons and mobility of what? Of holes. Depending on the type of material given. So if you are given a question and the type of material given in here, they are talking about N-type semiconductor. N-type semiconductor, we are not expecting, say, holes. We are expecting electrons. So we will not consider the mobility of holes here. We will only consider the mobility of what? Electrons. Likewise, if you are doing that of a P-type semiconductor, our majority carrier is the holes. Minority is the electrons. So if it's N-type semiconductor, we are not going to consider this formula. Please, are you okay? Now let's move on.
Yes, sir.
Now, if you have a situation like this, please, are we online or we are tired? Are we all online?
You're online.
We are all here, sir.
Okay. Now, when we consider something like this, we have, of course, a N-type to behave in this way for the conductivity, and P-type to behave in this way. And it's the same formula that I showed him here. Is that okay? I told you that when you're dealing with P-type, the electrons is not of importance. When you're dealing with N-type, the host two is not of importance. So when you look at here, for the N-type, the host is not important. It's only the electrons. So you consider the mobility of the electrons, concentration of the electrons, and of course, the charge. The same way as for the P-type, you consider the mobility of the electrons. Sorry, I think I've done a mistake here. This is supposed to be, someone should correct me. This is supposed to be what?
P.
H.
It's going to be H.
Proton.
H.
Host.
Hose.
Yes, the
Oh,
hose.
hose.
Then this one is the concentration of the what? Of the hose, and this one is going to be our charge. Is that okay? So please correct that in your slides. Now, the next thing that we have to look at is movement of carriers in semiconductors. But I think maybe it's almost time, so let me hold on to that one till we meet the next time. But the next time that we meet, we talk about the movement of carriers in semiconductors. We talk about concentration gradient. We talk about diffusion, electrons, a typical examples that we have, and we look at some equations. Then now we look at when you combine the two semiconductors, how it's going to behave. We have N type, we have P type, what is going to behave. And even after applying some EM field to A2, how is it going to behave? And I think Bismarck asks about an ohmic material. I have it here. We will talk about that one too. And supposing it's not an ohmic material and it's a semiconductor, how do we expect the voltage current characteristics curve to behave? That one too, we will look at it. And this is how it's going to behave, but we will discuss it and we'll look at the ways that breakdown causes. We have the avalanche, we have the Zener. We'll look at that one too. Then we'll look at the various applications of these diodes. They'll do some trial question. They'll do something called the load line. Then I will be done. So I'm done. Any questions so far?
For the
It's been
semester.
a long journey. No. This is one part. Oh, we have 4 parts. So this is part 1. So we do for part 2, part 3,
So
part 4.
Sir Rabbi, we were supposed to finish this one this
Very
week.
good. Today.
Okay.
Oh, but I will try. Don't worry. This, I think the
You
first part, I have a lot of slides in there. But the
okay?
second part, the slides is not that much. But I need time to
Okay.
explain that one, a lot of time. So
Okay.
you drew or now, you will cross it. Don't worry.
You.
So any
Yeah,
questions so far before I end the class?
Yes, no.
Okay. Because I think we'll be meeting for 4 times. Is that okay?
Yes, we'll be meeting for
So
4 times.
So I've divided the slides into 4 different
4.
series.
Okay.
So
Yeah.
I'll give you the first one after teaching. I start the second one, so I'll give you the second one. Then after
Okay.
that, I'll give you the third one. Then we will be done. Okay. So permit me to end the class. I'm already tired, so
Yeah, you are permitted. Okay.
we will meet one with the other. Have a good afternoon, everyone.
Good afternoon to you too.
Nice evening to you.
Bye.
Hello, sir. Is Castro with us? Sir Castro. Madam Felicia.
Omada. Yeah, good morning, Mr. Solomon. Hello, Mr. Solomon. Hello. Hello, Mr. Solomon.
Good morning, Doc.
Yeah, please, can you see me? Can you see my slide?
Yes.
Please, can you see the slide? Can somebody confirm for me whether you can see the shared slide?
Yes, please. You can see.
So let the others. I'm sure you're supposed to be 42. Let the others. Okay, so please, is the course rep on the plat? Has he logged in yet? Course rep, please, are you here? I think he's called Paul. Is Paul, has Paul logged in yet? I guess we can start, right? Okay, yeah. So good morning. My name is Clement Chin Adomako. I would prefer you just call me by CK. That would be fine. So we do away with the Mr., the doctor, and what have you. Yeah, so I am to take you in general organic chemistry. I think you've seen it on your platforms. And per the timetable, we are supposed to meet 4 times. I mean, we are supposed to have 2 online and 2 face-to-face, unless there is going to be a different arrangement. I hope everyone can hear me clearly.
Yes, please.
Yes, please.
Okay, thank you. Yeah, so that's my name. I'm a lecturer at SD College of Education, Asokoriko Florida. I think that is all the introduction I would like to give. And so without wasting my time, I would like us to go through our main topic for today, which is alcohols. In case anyone wants to ask a question along the line, please, you can do so. Please, Mr. Ernest, can you mute yourself? Please.
Yes, sir.
You can hear some noise. Thank you very much. Yeah, so in case you have any question along the presentation, please, you are free to do so. You can just raise your hand. If I am not calling, you can still come in with your submission so that we can have a fruitful discussion. Thank you. You are supposed to be 42, but I'm seeing only 23, now 24. But let's hope the others will join as we move on. Yeah, so we will be dealing with alcohols. And then we are going to build on what you did in Chem 108. We are building on that. You've already dealt with alkenes, and then the alkynes. You've dealt with them already. So sometimes you will need the knowledge that you had there also in the alcohols, more especially when it comes to the namings. Now let us do a little bit of a recap. So let me ask this, so anyone can just raise the hand and please answer. You dealt with alkenes, and alkynes. What distinguishes alkenes from alkenes, and what distinguishes alkenes from alkynes? Anyone? I want the class to be interactive, so please just feel free. You might not know everything, so we all share ideas over here. What distinguishes alkenes from alkenes, and alkenes also from alkynes, so that we can build on that to start our alcohol lessons? I see names here, so if nobody raised the hand, I'll just call randomly. I hope that will be fine. And when I call and you don't respond, it means you have only just entered and you have left and you are doing your own thing. You should be seen being participating. Okay, yeah. So Ernest Bojo, yeah, are you here? Ernest, on mute. Ernest, are you here?
I'm around.
Okay, yeah. So my question: what distinguishes alkanes from alkenes? Anyway, Ernest, are you chemistry or biology? Which is your area?
Biology.
Okay, but that is fine. What distinguishes? Okay, what distinguishes alkanes from alkenes and alkynes? Any idea?
Alkanes, they have a single bond.
Okay.
Then the alkanes have double bonds, and then the other have triple bonds.
Awesome. That is perfect. So you can mute yourself now. That is a perfect one. So for alkanes, we know they have single bonds throughout. Alkenes have the double bonds. Then the alkynes have triple bonds. And these are what we call the functional groups. So when we take alkanes, or when we take alkenes have double bond as their functional groups. Then alkynes have the triple bond as their functional group. What do you think is the functional group in alkanes? What is the functional group in alkanes? Moses, are you here? Yeah, I can see Moses Nyako. What is the functional group in alkanes? If alkanes are double bonds, alkynes are triple bonds, what do you think for alkanes?
Please, a single bond.
Okay, so don't mute, don't unmute, just still be there. Okay, so with this, Zachary, do you want to add something up? Okay, so Moses, let's dive a little bit. So you are telling me that alkanes, the functional group in alkanes are single bonds. Can you give me a little idea what functional groups are? What are they? Functional groups, what are they? Moses.
This is the carbon-carbon bond.
That is, I want a functional group in general. What do you mean by when you say functional group? What is it? Like in simple terms, what are functional groups?
That is the number of hydrogen bonds that are bonded to the carbon atom.
Okay, fine. Anyone with a different, you can mute now. Anyone with a different, Felicia, Isaka, what do you think of functional group? What are functional groups?
So please, I just joined. I don't know what you.
And so I'm asking what functional groups are. What are they? Functional groups, what are they? You did alkanes, and alkynes, right? Last block. Yeah, so what are functional groups? How do we define that? Zachary, I'll come to you. Go on.
So please, they are number of hydrogens bonded to an atom.
So that's the functional group. Okay, so Zachary, thank you, madam. We will come back to your answer. Zachary, what do you think? What are functional groups? Or what is a functional group?
Yeah, functional groups are atoms, are a group. It's an atom or a group of atoms that gives organic compound its characteristic chemical properties.
Awesome. That is a perfect one. So you see, I want us to stick to this and let us take Zachary's answer. So functional groups are atoms, a group of atoms or a bond that gives a particular organic compound its characteristic features. Okay, they are atoms or a group of atoms or bonds that gives a particular organic compound its characteristic feature. So what it means is, let's take an alkene. What will make alkene an alkene is the fact that it has a double bond, and it is only alkenes that has a double bond. So what I have that gives me those properties that I exhibit, what I have that gives me those characteristics that I exhibit, are what we call functional groups. When we take alkynes, alkynes have triple bond. So it is the triple bond that makes them alkynes. So when you take the chemical properties of alkynes, they will be different from that of alkenes, because the bond that we have in alkenes is different from the bond that we have in alkynes. Is that okay? So the thing that makes you stand out in a layman's term is what we call the functional group. So based on this, when we take alkanes, and somebody said the functional group in alkanes are the single bond, are you trying to tell us that when we take alkenes too, we don't have the single bonds there? In alkenes too, there are single bonds in addition to the double bonds. In alkynes, there are single bonds in addition to what? The triple bonds. If the alkane is only having these single bonds, and what you have, I also have it, how then do you tell me that is the one that is making you have those characteristics? Please, are we okay? Yeah, so my issue is about the functional group in alkanes. So sometimes you see in some books, they will go like alkanes alkanes do not really have functional groups. They don't, because the single bonds cannot be termed as functional group, because that functional group that you have there, all the other compounds are also having it. Please, am I clear?
Yes.
Yes, Doc.
To add alcohol. What is going to make alcohol is the presence of its functional group. That's what Ernest. You want to say something? Ernest, when I very much, so the moment you come, you need to talk. That is that okay? So when we take the alkenes, it is the double bond. When we take the alkynes, it is the triple bond. Now today we want to look at alcohols. So when we talk of alcohols, what should we see in the structure of an alcohol to determine that this is an alcohol? So there should also be a functional group over there. So when we talk of alcohols, they are compounds whose molecules have what we call a hydroxyl group. I hope you'll be taking some notes. Once I'm done with the class, I'll share the slides with you on your platform. There. So please, those with notes, just try and take some notes down. So alcohols are compounds whose and that is hydroxyl group. And this hydroxyl group is attached to a saturated carbon atom. You did saturated carbons. Those were the alkenes. Then they all saturated with alkenes and alkynes. Okay, so that's the second alcohols are compounds whose molecules have a hydroxyl group attached to a saturated carbon atoms. So that is the simplest definition. Okay, so this is it. I hope you can see the cursor moving. Can you all please see it? Somebody should just answer me.
Yes.
Okay,
yes,
very good. So thank you, sir. So this is the OH that I am talking about, and that's what you call the hydroxyl group. Please forget about the opposites and the ethers. That will be the next thing that we'll be looking at once we are done with the alcohols. So this is the OH group that makes it at the alcohol, and that's the functional group. The R is the alkyl group. Is that okay? The alkyl aspect. So the R could be methyl, it could be ethyl, it could be propyl. Is that okay? So that once you add it to it, it gives you the name. So what makes this an alcohol is the presence of this OH group. Okay, now we want to look at the general formula for alcohols. As you did under alkanes and the alkenes, I am sure and certain in my mind that during your lessons in the alkanes, you look at the general formula. Is that okay? Where you had the CnA2n plus 2 for alkanes. Then you also look at CnA2n for alkenes. Then for the alkynes, you look at CnA2n minus 2. I guess you looked at all this. Now, when we take our alkane and our alcohols, this is their general formula. CnA2n plus 1. Now, when you look at just this aspect from the CnA2n plus 1, which of the other three general formulas does it really resembles? CnA2n plus 1. Compare it to the alkanes, and the alkynes. Which one does it really resembles? I'm not saying it looks the same, but resembles. Which of them? Somebody can unmute and just speak. Which of them do this alkyl group resembles? Forget about the OH. The CnA2n plus 1 Which of the three alkanes, and alkanes are they resemble? Okay, yeah, somebody has omitted. Bashiru.
Yes, sir. It
Yes.
resemble it resemble alkanes.
Very good. Awesome. So it resembles alkanes. So if you check the alkanes, it was CnA2n plus 2. And this is CnA2n plus 1. So the only difference is that we are having a shortage of just one hydrogen. Is that not it? So if it was alkane and it would have been CH4, here it's going to be CH3. If it was ethane, which will be C2A6, this will be C2. Yeah, Mr. Lord, anything? Lord Kingsley, you are unmuted. You want to say something? Okay, Ibrahim, please mute. Good. Yeah, so that is it. So it means that when you want to name alcohols, then you have to still have some knowledge in the alkanes. So the same way we named alkanes, we are going to use the same way, just that we'll be adding some slight differences to it. Is that okay? So please just bear that in mind. So this CnA2n plus 1 is what we call the alkyl group, the R group. So as you are seeing, O or R, so the R is the CnA2n plus 1. Then the OH, like I said, is the functional group that gives you your alcohol. So where R is an alkyl group, or it can be aryl group. The aryl group means it can be a ring. Is that okay? So when you have them in a ring like this, you have the phenol and the others. Perfect. So we move on. Yeah, so examples of alcohols. But before we move with the examples, I want us to look at types of alcohols. So there are 3 types of alcohols. We have what we call the primary alcohol, we have what we call the secondary alcohol, and we have what we call the tertiary alcohol. So these are the 3 main types of alcohols that we have. What distinguishes each of them? Now, when we talk of a primary alcohol, this is a primary alcohol, as we can all see. This is a secondary alcohol, and this is a tertiary alcohol. So a primary alcohol has only one alkyl group. Is that okay? A primary alcohol has only one alkyl group attached to the carbon atom with the OH. So that is where the key point is. So let me take it again. What makes this one a primary alcohol is that here, this is what we call the condensed structure, the condensed form, or the molecular formula. Is that okay? The molecular formula, you put everything together. The condensed form, if you want to draw the structural formula, that is when you show the bonds. So this here would have had H here, H here, H there. That 3H would have spread out. And that's what we call the structural formula. This carbon, this CH2, this very carbon, is the one that is bearing the OH. Is that okay? So it will have OH at the top or down, it doesn't matter. Then it will have the other 3 hydrogen, the other 2 hydrogens spread around it. Note that a carbon is a tetravalent element. Tetravalent in the sense that it has 4 atoms bonded to it. What makes this one primary alcohol is that the carbon having the OH is having only one carbon attached to it, like this one, ethanol. Is that okay? It's having only one carbon attached to it. And that is, yes, Frank.
Please, yeah, the cursor is moving somewhere, and then what you are showing is also somewhere else.
So
And then,
I think it's because okay, hold on.
Okay,
is it okay now? Is it okay now?
Fast.
Is it okay
yes,
now?
it's okay. It seems you are also moving very, very fast.
Oh, okay, that is fine. That's awesome. So I'll take my time. Thank you. Okay, so now I want us to look at types of alcohols. And I'm saying that there are 3 types of alcohols. There's what you call primary alcohol, there's what you call secondary alcohol, and there's what we call tertiary alcohol. I hope everybody is clear on that.
Yes, Doc.
Yes, Doc.
Very good. So now I want to explain what makes something a primary alcohol, what makes something a tertiary alcohol, and what makes something a secondary alcohol. So I'm saying that example, ethanol is a primary alcohol. Why? And this is the reason. Look at this carbon. As you can all see my cursor on. This carbon is the one bearing this OH. When we spread it out, when we put the hydrogens on these carbons, there will be one at the top, one down here, then the other side will have the OH. Then when we spread this hydrogen on this carbon, there will be one at the top here, one here, then one there. This is what we call the structural formula, the structure. The structure is where you show the bonds. But what we have here is called the condensed. So instead of showing the H here, showing the other H here, showing the other H here, you just put it as H3. What makes this one a primary alcohol is that the carbon, this very carbon, having, please let me pick a call. Your call rep is calling me. A second. Yeah, Paul. Yes, sir. Hey, yeah, enter the down. Me was one of you. Yeah, enter the down. Please check on the platform and enter. Your people are there, please. Maybe you have entered the wrong one. Please check the one you were provided. A lot. We have almost let me check. We have almost everybody is here except you. 40 people are here, so please check. I beg you. Thank you. So thank you. Yeah, so your course rep seems to be lost. He's now calling our time, but I've told him we're already on this platform. I guess you were given a platform.
Hello, sir.
Yeah, each platform, each course has. Yeah, please go ahead.
Sir, you are in the wrong. You are in the wrong link. You have done the wrong link because Kofodia sentence.
I hope excuse me. I hope we are using the right link.
No.
Yeah, is this Wesco or online?
No, this
Sir,
is
you are supposed to join
this online.
Center.
Online.
You are supposed to join
online.
Kofodia Center, but this is not Kofodia Center. This is Wesco's.
This is Wesco.
So you are supposed to join this for Kofodia Center.
But sir, you joined
the link that we joined through is Wesco.
Hold on.
This slide is not Kofodia. Kofodia people are waiting.
Really? Is it that I have joined a wrong link?
Online.
Yes.
Yes. This is
Hold on a second, please. Wow. I thought
but we are enjoying your class too.
Go enjoy my class. You go to your class. Alto is my boss. I beg you. Oh, really? Sorry, let me leave. I think I use this link. I'm going. Bye bye. Oh, let me leave as quickly as possible.
Okay. Yes, I'm for Kofodia and been waiting for you.
Hello, good afternoon.
Afternoon, sir.
Good afternoon, Doc.
How are you?
By the grace, you are doing great, and
you are fine.
Yeah. All right, I'm here to teach.
Good afternoon.
My session had to be rescheduled because of ongoing follow-up program. So we need to reschedule my meeting.
Sir, we didn't hear you.
I'm saying that I am out of coverage area, so I'm just joined to notify you that we need to discuss and reschedule this meeting. Time.
Okay.
So those of you who are here, let's think through and propose a different day for this.
Hello,
session.
sir.
Yes.
Sir, we can reschedule it, but the date tomorrow. Some people have class. Monday, natural products also take chemistry class. I don't know when that time will come out.
So the natural product, I'm the one handling the natural product,
Very well.
and that one is elective. So I will find a way to manage that smaller number as
Okay.
compared to this amorphous group where they are
Okay.
different programs.
Okay.
And so I will prefer we make use of the Monday, 6 p.m. That's my proposed time. Monday, 6 p.m.
All right, colleague.
If it's
Sir
okay
Okay,
is
with
sir.
the
proposing
class,
Monday.
yeah.
Yeah, I think it's okay.
Monday is okay, but the time will know. Say it's 9
Please,
grams for
what
your
time
class. I
Monday?
do.
Yeah, dog, agree.
So,
All right.
Sir, 6 o'clock
What
is
time?
okay. 6 o'clock is
But
okay.
then, but
At
then,
least
but then,
it's okay. The time is
but then,
okay.
any student or group of
Tomorrow
students
6 p.m. is okay.
who have problem with a Monday. Hello.
Sir, we are listening.
Yeah, we are listening.
Yeah. So any individual or group who have an issue with a Monday, they should just private message me, and then I will find a way to attend to them. Hope
All right, sir.
that's
Sir,
okay.
I believe we will discuss and we'll get back to you with a Monday.
That,
But
that's fine.
tentatively, Monday has been approved. Any change will notify you.
Yeah, but I think Monday is okay.
All right. But then, in order not to make this time go waste, can you join that work group?
Okay.
That she is teaching the UCC Center online. So if you can join that group and then have a fair idea, because as you can see,
All the centers are having class. Wesco is having needs, Kofodia is having needs, and then I think some other centers too, with the exception of those having online. Zenith
so
is
so
tomorrow,
join
so we can join the other classes links
yeah
on the
so join the
platform.
other classes, please. Don't make this time go waste. Join the other classes and then it will help you so that when we meet on Monday,
All right, sir. You do that.
all right.
Thank you.
Doc, what about we that we are offering natural chemistry? You said Monday. Won't
Yeah.
it
So
crash?
we are on a hour for chemistry. Okay. So I will join that one with you. We'll have a discussion there.
Okay.
Take a decision.
Okay, sir. Thank you very much.
So the
Hello, colleagues. Good afternoon. And what is happening is dog coming. Let's communicate more. Is dog coming? Any idea?
Hello. Hello. Please, is anybody here? Hello.